Okay? And we have here today a robotic arm. It's made online, not by me. A group of people somewhere overseas did that, and it's just cool to see it. Okay, so in your Georgia view, I posted the scripts because some of them are too long. One of the scripts, maybe you gotta write it by hand, but it's a short one. So cantilever beam, again, this is a course, needs some physical kind of understanding, like this kind of a problem. In, you know, the guys who are signing up for the course next semester, strength of material, what's called, mechanics 1, statics, mechanics 1, we have a course next semester. In that, we'll talk a little bit here. So what you're seeing here, like when you see a wall, then you see this, it's like a solid wall. That's what he's trying to tell you. So I'm trying to be basic here. Then you have a beam, imagine it as a diving beam, you know, the one where the divers jump on it. So that's a wooden beam. Then you have a force. Let's say that's the weight of the diver. Let's say this is the diver. So that's his weight converted into force. Now, it's in the steady state. There's no force on it at all. When you apply force, obviously you will bend it at a certain angle. Now, to be able to see what happened to the displacement on the bar on the x and the y axis, you will put a strain gauge here, like kind of a sensor, that the sensor elements inside, they will bend a little bit, but you can't see it in hand. Then he will tell you through a circuit what's going on in curves as an x and y representation as we see here. So that's the physics behind it. So if you bend it, like it will go like this maybe. Now you want to draw the displacement, like what's the beam displacement on the x-axis and what's the beam displacement on the y-axis. Then you take the dots. If the beam with no force applied on it, then it's going to be straight line, like a straight line. So there's no motion on the y-axis. On the x-axis, it will never move, so you just move on the y-axis. Then you can see your beam is moving, like from 4 millimeters or centimeters to 3 to 2, and so on. So that's what we're trying to do here. The course or the code is ready. We're just gonna run it and go through it. Maybe I'll try to ask you to change a couple of things and see how the result would come out. Now, in this exact example, we have an equation for y. So we have x and y. Y is represented as minus, open parentheses, x to the power of 4 minus 4x to the power of 3 plus 6x squared. So that's the displacement of the beam on the y-axis represented in equation. Now, x capital in this case would be small x divided by L, or the length of the beam. Now, E is the material property that we know it as modulus of elasticity. It means how elastic is the beam. When you bend it, does it break right away or come back? How fast it come back? So that's just a material property. It's okay if you don't understand that because you didn't take the course of material or strength of material course. Now, as you are under no load, y would equal 0. When you have a load, y displacement would be corresponding to the amount of force. Now, the question is, what is the shape of the deflection curve when the beam is in its loaded condition, and how does it compare with its unloaded, perfectly horizontal orientation? So we're trying to draw the curvature of the displacement of the beam based on the displacement equation that we got, which is y equals that equation. Now, the author is giving you tips, as we learned before. You gotta think it out. I don't want to ask you like, hey, go ahead and try to solve it, but we're trying to walk through the software here. So as the progress for the program, you gotta think about it, how you're gonna approach it. So step 1, select the distribution of the x points from 0 to 1, where the deflection to be plotted are to be determined. So now you decide x equals 0 to 50 with an increment of 1. It's like you're saying the length of the bar is 50 meters, 50 centimeters, any convention that you choose. Now step 2, what you want to find the deflection y, or the displacement of the beam on the y-axis. That's the naming of deflection. At each x, there's a typo here by the author. So y at each x. Now, YE is the unloaded position of all points on the beam. So YE equals 0 means the displacement of Y when there's no load. We know that when there's no load, there's no motion on the Y-axis, so it's 0. And the Y itself is a factor, or it's a factor of X, or the values of X that we have here. So back to the equation that we had in the slide, you're trying to change this equation into a MATLAB format. That's what you're doing here. So Y would equal minus X dot to the power of 4, like either X 1 value or 100 values, you gotta have it to the power of 4, minus 4 multiplied by X to the power of 3, plus 6X to the power of 2. So basically, he's just representing the equation that we saw in our slide. Now, the third step, you gotta plot the results to illustrate the shape of the deflection beam. So you gotta show X and Y, how the beam is moving on the X-axis and Y-axis, as we saw in our drawing here. Now, of course, you say plot for X 0 to 1, and for Y 0 and 0, have a dotted line representation, then draw X and Y, and you decide your line width. Remember the properties that we talked about before, how to assign them. Now he said the axis, so he's deciding how the axis grading is going to happen. Now 0 to 1.5 on the x-axis, and it's going to be minus 4 to 1 on the y-axis. And write down the title, deflection of the cantilever beam. So you're writing the title here. Now the x label will have x and the y label will have y. And show me the legend and write down unloaded cantilever beam for the first one and uniformly loaded beam for the next one, and stop. Okay, let's go ahead and run it. So if I run it, you can see here I have a dotted line for the unloaded Y. So here you can imagine this, there's a beam, but here there's no physical representation of beam. You're just representing data, right? But still, the curve is looking like as if the beam is being bent. So when there's no load, the beam is at 0. There's no X or Y motion. While if the beam is loaded, there's an X and Y motion. So it will be a decrement on the Y-axis and a decrement on the X-axis. Like at this exact point, what would it be? It's not showing me exactly. So you could say here 0.0, 0.25 maybe, or 0.15 on the X-axis, and minus 0.6 on the y-axis, and so on. So you draw the points in a solid line. Then you have your legend here, the load in red, unload in blue, and you have the headline of the drawing. Now, it's showing me the y-axis. What's the standard here? So he's showing me from minus 4. Well, I don't see minus 4. I see. So I want to limit the y-axis to show me from 2 to minus 2, and the x-axis from 0 to 1.2. Can you guys play with the code and do that? Try to play with it and see if you can achieve that. You need to read the code and see where did he define the range. So I'll run it again to see the standard way. So you can see 0 to 1.5 on the x, and 0 to minus 4. So find those. 0 to 0.8, and the y minus 2 to 2. Now if you change the dots, the 2 dots into O's, so he show you only point, like only O at each point you called out. You see at 0 and 0, we get an O. And at x equals 0 and y equals 0 and x equal 1, he had another dot. So it's like you draw a line between point A and point B. That's what you did. So when we understood the logic, it's easy to make the program do what we want. That's the concept. Okay, that's enough on this. It took more than it deserved. Now, the next one, we have a simple circuit. How many of you know about circuits, either as a hobby or in courses? You do? Okay. So at home, would you be fine lighting up an LED? You know, like basic LED. I'm not saying like something ready. It's simple, guys. I know I'm being very simplified here. I apologize for those of you who know it. Positive, negative. Now, to light an LED, assume it's a bulb, but it's an LED, right? Now, it has a positive side and negative side. The old LEDs, the one in your grandpa lights, the small one, the bulbs, like the ones in the cars, those, they don't care either way. You connect it here to here or here to here. Either way, battery will make it work. Now, you know those, maybe you try in your childhood. Some of them, if you get a 1.5 volts battery, double A battery, by the way, is 1.5. Triple A, I'm not sure, honestly. Triple A, what would it be? 0.9, I think. So we call how much capacity in this using the unit volts, so 1.5 volts. But battery have volt and have current, like how much. The volt alone will not help me. I gotta make the current, the electrons to move through the tungsten wire here to light it up, you know? Voltage alone is not enough, but you gotta match it. Like too much voltage will burn it, too much current will burn it, you know? Don't go deep into it if you don't have the knowledge about it, but you will learn about it in your circuits course. I believe you have it in your curriculum. Now, in LEDs, the one you see maybe in your, I don't know, in your applications, whatever game toy you have, LED look like this. If you hook up, let's assume this LED can handle 1.5 volts and maybe 0.008 amps, which is the unit for calculating the current. You could burn it. Not to burn it, you need a resistor, something like kind of a valve to reduce how much current going into him, you know? So like this bulb will work at 1.5 volt, but he can't handle too much electron through him, he will be burnt. So you put a resistor to kind of ease down the current. It's like you have a paper valve, but if you push too much water into it, it will crack. But if you kind of reduce it into a smaller kind of passages, then maybe the paper will be able to hold it. Okay, so now we need, in short story, resistor symbol is like that in circuit. Well, it's like this. So electrons, let's say, go from negative to positive, I'm assuming here. So electrons are going, they go through the resistor, so electrons will be more regulated, if you will, and they will go through the LED, different concept than the tungsten lights. Electrons go, you will light up the circuit, and the electrons will go back into the source, and on until your current is getting weaker and the battery is off. So there's an equation for that called an Ohm's law. Ohm's law is saying voltage equals resistance multiplied by current. Voltage, resistance, current. Now, if I told you create a MATLAB code for me, one of the really painful problems when you have LED, some of them can handle little current, some of them can handle strong current. So you got to calculate to know what is the best resistor that match this kind of LED to give him the right current. So using this equation, if I told you make a MATLAB program for me, I tell him how much volt I have, I tell him how much current he can handle, he will tell me what kind of resistor I need. Because resistors in the market, you can have it 400 ohms, 200 ohms, 1000 ohms, so really confusing. So I would say, okay, from Ohm's law, like this is Ohm's law, scientist called Ohm. Now, resistance R would be voltage divided by current. That's the equation holding it. Now, if I told him, okay, my voltage is, in this case, 1.5 volts, and the current that this one can handle is 0.008 of an amps, you know? So, you know, in the main plugs, I think it's 20 amps. Like that one would shock you badly. And in some cases, it's 1 amps, depend on the situation. So you got to create for me right now. Go ahead and use your best knowledge to create for me a program. We will start with simple. He will ask me, what's your voltage? Like, what's your V? Then he asks me, what's your I? Then he will tell me your R that's recommended would be this value. Go ahead, should be a couple of lines. But the next stage, you will tell me in menus, like after you're done with this, you tell me in menus, okay, your voltage is this, or this, or this, Then he asked me again in a menu, your current, is it this current or this or this? Then I choose, okay, this is my voltage, this is my current. He should take them and find the R and display it for me. But let's go for this. So, that being said, V input, you input your value and save it in V. I equal input circuit current, put it in I. Then run your equation, resistance equal voltage over I. Display the recommended resistance is, then display num to string R, or do it the way I just described. If you run it this way, circuit voltage is 3.5, okay. 3.5. What's your current? 0.008. The recommended resistance for your LED is 437.5 ohms. Now, to create menus, for the favor of time, we gotta skip that. I mean, we're not skipping menus, but I'm gonna do it myself. So you say A equal menu. Remember menu, then you write what you want as the headline of the menu, in this case voltage. Then put your choices. Choice 1, 5, choice 2, 3.5, choice 3, 1.5. Now I say if A equals 1, it means choice 1, then V would be 5, because choice 1 value is 5. So when I choose 5 in the menu, the program will not know I choose 5. He know I chose number 1 in the selection. So I'm gonna bring it back as a 5. If A equals 1, like the first value, make V to be 5. Else, if A equals 2, V is 3.5, and so on. Then you end. For B, the current menu in this case, 0.1, 0.008, and 1. If B equals 1, then the current would be 0.1. If B equals 2, the second choice, then I would be 0.008. If B equals 3, then you end. In this case, what would you do? Of course, comment out these. They shouldn't be part of the program in this case. Now, if you run it, so you get, what's your voltage? 3.5. What's your current? 0.008. And he said the recommended resistance in this case is 437. That's how it's done. So there is a long, lengthy one in your book for electric current, but I thought that simple one that I just created is more making sense to you, because even you guys barely handling this. How come that one? That one is too complicated for you, honestly. You can go through it, but I wouldn't ask you about it. This is the code. If you want it, you can run it in your program. You should get kind of analysis more than a research application than it is for your entry-level state. For a free-falling, of course, we have a free-falling object, y equals 0. Now you have the acceleration as the second derivative of y. Velocity is the first derivative of y, which is gt. And the y would be half gt squared. Of course, if you had it in your physics class, then you know what's going on. If not, then I don't blame you. I wouldn't ask you deep physics as it is here. But he's trying to say what is your y in meters when the time is 5 seconds of free fall for the 3 cases. And what are the terminal speed in meters per second? Is the terminal speed reached at t equals 5? So it's a deep physical problem in this case. But I'm going to run it for you for the sake of you seeing the code. So if you run it in this case, you can see there is speed versus time, or time versus speed, based on your calculations. So in this case, you are calculating the initial value of y and the final value of y. What's your launch angle for your project, for your free falling, and at what time should this velocity be and should this displacement be. So you're seeing displacement, acceleration, and velocity all in one graph. That's the whole point. And here you're comparing your results. You can dig deep into that if you are thinking that this is something you know physical-wise, and I would be happy to help you for any portion. Again, here we have a projectile. You have the vertical velocity and the horizontal velocity. U is the horizontal velocity, and V is the vertical velocity. Then you have here the derivative of U and derivative of V, which is the acceleration in this case, represented in those 3 equations. And the location of the projectile initially at 0 at x and 0 at y. He launched the speed at the velocity v and theta angle. So he will ask you the script to put the theta and the v, and he will calculate the projectile motion. Just for the sake of demonstration, I believe this is too advanced for you. You shouldn't Just think so much about it. Initial angle, 45 degrees. I'm trying to put in 45 degrees initial angle. What's your initial speed? 30. Now, for the robotic arm, there is in the community, you can find some MATLAB-based programs that you can use. I pulled one called Robotics. I already pasted it for you. But remember, those, after the first 3 scripts, there's many weird files. Those you need them because this program is not only on MATLAB. It's using graphical user interface a little bit. That's what I called you as MATLAB guide. But he's just creating figures and moving the arm of the robot based on the directions on X and Y, Z directions. And you can see an animation of the robotic arm here in case you're interested. As soon as you run it, hopefully you will not have any code problems, but it's a very long code. You have 4,600 lines of code. So, but it's good to tell you how strong is MATLAB. Let's run it. So here you choose links, you know, like every arm of the robot, like your hands. This is link 1, this is link 2, this is link 3. So you would say, this link, on what angle should it be? What rotation should it be? This link, should he have rotation? What extension? What's the angle between this link and this link? So you're choosing, you want it as a prismatic, like constant, or rotation. Second link would be rotation for me. Third one is rotation if I want. Then I choose, I want it to be drilling or welding. It's like he's mimicking a robotic arm that's doing a certain drilling or welding. So I ask go, and he's calculating because it's a heavy program. Then he's generating a robotic arm following a certain procedure, what angle and what speed, and when he should be welding and when it's not. You can imagine it as welding the body of your vehicle on an assembly line. You got to go through this line at a certain speed, otherwise he will break in terms of welding. I thought we'll have more time to play with it and ask you guys stuff to change, but it's a 4,000 lines of code. Imagine how simple this thing, but 4,000 lines. I told you, programs will get very complicated quickly as you're doing stuff, but not as complicated as it looks. It's very useful, very functional. So you will never regret learning MATLAB as an engineer. There's always unlimited possibilities, and combination with Simulink that we're going to learn a little bit quickly next time about it. Then you know that the sky is the limit. You can go from universe analysis into computer analysis, into robots, into even maybe analyzing the behavior of your plant or your bird.